Okay, let's continue with the program verification stuff. Okay, today we'll do a little bit more complicated rule. Let me just restart my slides over here. Okay, we talk about the assertions being weaker versus stronger. That's what we began with last time. So now we're going to present a series of the weakest precondition rule. So let's just review what a weakest precondition is. So how do we judge if your program is correct? The way to do it is by the given precondition and postcondition, I have to somehow calculate what is going to be the weakest precondition for my implementation code to establish the desired postcondition. Okay, that's kind of the first step. And then I want to see my existing precondition is no weaker than the weakest precondition. Okay, that's kind of the two steps you got to do. But we'll do examples. The first rule that we talked about last time was simply like this. So let's say your program is simply as simple as just a single assignment. I'm trying to assign an expression E into variable X. After this, I want to establish some postcondition R. So now WP calculation over here is going to tell me on the right-hand side of the equality is going to be another assertion. So this assertion over here is going to represent the weakest precondition for my implementation to establish the postcondition. Okay. So now let's just do one exercise in full detail. Okay. That's something you're expected to do by yourself, of course. Okay. Let me just open a new page, and then we'll do one complete example together. Simple program. Let's review the one we did last time informally. Okay. First of all, let's talk about program. Let's say you're given a program like this. Let me just simply say, remember increment by 9 example, right? Increment by 9 example here. So we got specification, we got require, and we have ensure. Okay? And also we got some implementation over here. Implementation is simply, let's say I is assigned to I plus 9. And then ensure is to make sure I is larger than 13, for example. Okay, now what should be the precondition, right? Let's say if I simply put a precondition over here, I is greater than 5. Okay, that's what I have. Again, so now this is your given problem. This is a problem. The question is this program correct or not? So this is a question. Okay, so if you're given this question here, what should you do? Okay, I'm going to show you exactly the steps you're going to follow. When the program gets more complicated, you're going to follow also the same steps. You just say the WP rule you're going to apply will be a little bit more. Okay, but we'll just make sure you understand the steps first. First of all, simple. Translate the program into Hoare triple. Translate the program into a Hoare triple. And that one is very straightforward. Basically, you have two pair of curly brackets over here, and then you're going to put a precondition over here, you're going to put a postcondition over here, and then you put a program over here. Okay, let's do that translation very quickly. Precondition, I larger than 5. Postcondition, I larger than 13. And the implementation there, I is assigned to I plus 9. Done, first step. Okay, let me again just highlight what you should really notice. I larger than 5, I larger than 5. And also, let me use pink over here. I larger than 13, I larger than 13. And also whatever that goes inside the do block is the implementation. Today we'll actually show you that it can get as complicated as you got if then else, also loop. So that will make things more complicated. So now second step. Let's state what we really want to prove. Okay. First of all, let's now look at this part. Let me break this down into two parts over here. So let me use maybe a different color. How about blue over here? I want you to look at this part first. This part simply means I'm going to execute this block of code, which is a simple assignment. What I really want to establish upon termination is I is larger than 13. Okay? So now I want to make sure the weakest precondition for this particular block of code to establish this postcondition here is somehow consistent with the existing precondition. So what do I mean? I'll write it down. So I want to make sure existing, let me say proof that the existing precondition, which is I larger than 5, is no weaker than the weakest precondition, okay, over here. So now we have I is assigned to I plus 9. And then for me to establish I larger than 13, okay, again, I'm going to use color to really show you so we don't lose the picture. Larger than 13 over here. And also we have the existing precondition. Okay, that's second step. You want to know what you want to prove. Third step, let's calculate the WP. So usually the third step is the most complicated one, but it's really mechanical. So if you know the rule, it should be, it's doable. So this one is very trivial. Let me just do that. Okay, step number 3, calculate the WP for I is assigned to I plus 9 to establish I larger than 13. Okay, what is that? In order to calculate this, you have to see how complicated is your program over here. In this case, it's very simple. You just want to see what's the rule you're going to apply. If you look back in the slide, the only rule we have taught you so far is this rule over here, assignments. Okay, let's just do that. Okay, now I'm going to repeat that and then I'll show you the equational style of doing this. So let me start with, I want to calculate WP for I is assigned to I plus 9. Upon termination of this, I'm going to establish I is larger than 13. So what's the weakest precondition for that? So now I'm going to say this is equal to something else. Now in the equal sign over there, I'm going to give some reason which rule I'm applying to. Okay, so now it will be sufficient if you simply say WP rule for assignments. Okay, just like that. So after this, we can simply say now, simply put the post condition over here, simply put it there. Okay, and then I know that this I over here, let me give you some intuition here. This I over here is to say this is a post state value for I, which means upon termination, the post state value for I must be greater than 13. But now we want to see how can we make a connection between the pre-state and post-states. The way we do it is by saying the post-state value over here is substituted by the pre-state value plus 9, right? Because this I here is the very pre-state value, I'll say pre-state. Okay, that's kind of intuition into the rule. So now I can say that again, this is I larger than 13, the post condition. And then I can simply say I'm going to do some replacement. And I'm going to say for every occurrence of the post-state value I, substituted by, now I can make it more explicit by using old I. I can say I with subscript 0, I0 plus 9. Okay? And now I can do the substitution. Okay? Now, this will be equal to, you can say simply substitution. Now, this is going to be I0 plus 9 larger than 13. Okay? Everybody see it? Okay? You can see that every occurrence of I is going to be substituted by the pre-state value of I plus 9. So I simply substitute this I over here by I0 plus 9. That's what I did. Okay? Now let's simplify this expression a little bit. So now after some simplification, I have I0 over here larger than 4. Okay? So now what is this? This is the weakest precondition. Okay? So now let me just say that again informally. But that's exactly what we are calculating. So you should really know this is really what we are calculating to begin with. Okay? So now let me just annotate this. This one over here. This is a WP for I is assigned to I plus 9 to establish I larger than 13, which is the original post condition. Guys, any questions so far up to now? Okay, that's how we calculate the WP, right? So now the final step, step number 4. Step number 4, I'm just going to put it here, okay, just running out of space. Step number 4. You want to prove that, remember what we want to prove. Let me just highlight again. This is what you want to prove. You want to prove that the existing precondition is no weaker than the one we just calculated, okay? How do we specify that logically? You're going to say that what's the existing precondition, the green one? I larger than 5, does that imply so here this is I0, but when the context is clear, you don't have to mention I0. So now it implies I larger than 4. Okay, again, this is the existing precondition. And this is the WP that we just calculated from step number 3. Okay, now, can you say this is true? In this case, I larger than 5 implies I larger than 4. It's true, right? Good. Yeah, this one is obvious, so you don't have to do any further proof to show me. But you will see that when I give you exercise on Monday, you will see that in some cases you got to do a little bit more equational reasoning, like what you did in 1090 or 1019. Okay, that's something you have to do. Okay, so now this one here, it holds in general, so I would say proved. Okay, and now we are done. Guys, any question here? Are we okay? Okay, now, let me just show you another one. Remember, we also consider another possibility. Let me just, again, use a different color here. What if I change my program a little bit? So this will become a second question. So now, what if I simply say I larger than 3? That's the only change I make. So rather than having the existing precondition being I larger than 5, let's say it's now I larger than 3. Now, is the program correct though? Think about what's gonna be changed in your proof. So now that means over here, what I'm gonna consider is I larger than 3. That's the existing precondition, and the postcondition and the implementation stay the same. Now you want to prove that the existing precondition now is I larger than 3. Is that no weaker than the WP over here? So the implementation over here, the postcondition stay unchanged. So step number 3 is exactly the same. Now, when we go to step number 4, we gotta change the left-hand side, right? Because now the existing precondition is I larger than 3. In this case, think again. Does I larger than 3 imply I larger than 4 in general? No, right? In this case, I would say I'll be more convinced if you can give me one example, which will satisfy the left-hand side, but not the right-hand side. Okay? So over here, you can simply say no. For example, when I is equal to, what about 4? Because when I is equal to 4, 4 larger than 3 is true, but 4 larger than 4 is false, so you will get false. Okay? That's how you disprove it. Any question about these two examples? So later on, doesn't matter how complicated the program it might be in the do block, you're gonna follow exactly the same pattern over here. Exactly these 4 steps. Okay? But step number 3 is the most sophisticated. You gotta know which rule to apply for the weakest precondition calculation. Okay? Okay, if no questions, I'll move on to the next. Okay, so so now this is simply to say, now how do we prove that? Let's say this is a Hort triple, right? Given that the precondition is Q and the postcondition is R, and the implementation is simply a simple assignments. How do we prove that this program is correct? That's exactly what we did. So this Hort triple here, which is called the correctness predicates. This can be proved true if and only if the existing precondition Q is no weaker than, that means it implies, the weakest precondition for X assigned to E to establish R. Okay, that's exactly what we did. I'm just making that very formal. Okay. Okay. And you will see that we actually got 2 exercises over here, so they are very similar. Okay, I'll just let you follow that. So this one, I simply leave the precondition here empty, which means let's leave that until the last step. Doesn't matter what the existing precondition is. You will see that after this calculation here, we will see that the weakest precondition is simply just true. Okay, that means actually there's nothing that's going to be weaker than true. True is the weakest assertion, as we said. So now that means it doesn't matter what you put in the question mark over here, it will always be correct in this particular case. Because I'm trying to do increments, of course, after the increments, the post-state value is always greater than the pre-state value. Okay? So this one just to exercise your ability to apply the rule. If, let's say for this one over here, let's say for this program here, what will be the weakest precondition in this case? If you can calculate just in your mind over here. Let's say the implementation here is x is assigned to x plus 1. We are trying to increment. And what we want to establish upon termination is x value must be 23. What's the weakest precondition? Equal to 22, right? Exactly. You just substitute x by x plus 1. So that means x plus 1 is equal to 23, which is equivalent to say x is equal to 22. Exactly. Okay? So these are the simple cases. Okay. Okay, you can just go through the case over here. Okay. Okay, that's about the WP rule for assignments. That one is very easy. But that's kind of the basic building blocks as programs get complicated. Okay, now, second one. So this one is slightly more complicated. Okay, now let's try to understand what's really the thing over here. Okay, let me just put it down on the iPad, and then I'll show you. Okay, let's write it down. So we have what's the WP weakest precondition. Remember, the weakest precondition is going to take two arguments. The first argument is going to be a program, right? It's going to be a program. And the second one here is going to be the postcondition. Usually we just say R over here. So now the program is more complicated than a simple assignments. So here is if some Boolean condition B, then we do something. We just say S1. S1 is simply any program, just any program. Otherwise, we do program 2, okay, and end. Of course, you can easily translate this to whatever syntax of your favorite language. It does not have to be IFO, okay? So now, how do we calculate the weakest precondition for this? The only intuitively the difference compared with a simple assignment is, in the case of the simple assignments, you do the updates unconditionally, right? But now, what's the difference is, you only do the updates for S1 when B is true. What would be the circumstances for you to do S2 then? When what? When B is false. Exactly. That's exactly the meaning for if then else, right? So now what we want to do is something like this, okay? Now, we can say that it's going to be equal to something, okay? I'll give you some little bit hints, and then I will ask you what should be the connection between them. So now I know that I can either end up doing S1 or S2, but not both, either one, right? Because that's the, if this is true, I will only do S1, but not S2. If this is false, I'll only do S2, but not S1. One or the other, but not both. Okay. So now let's say this. I want to somehow calculate the WP separately, separation of concern. I can say, what's the WP if I happen to execute S1? In that case, S1 is going to establish R. Okay, that's one case. And also, I got another WP. You know what? Let me just leave a little bit of space for myself so I can show you a little bit more clearly. Okay. First of all, I'm going to say WP for the first branch over here, S1 to establish the common postcondition over here, R. That's one case. And then I also got another WP over here, which is for the second branch, S2 to establish R. However, this is kind of lacking the context over here, because when I say, I want to say S1 is going to establish R, I'm missing some information over here, because when I'm actually at this point to execute S1, I have some extra information I can make use of, which is, if I reach S1, that means B must be true. Otherwise, I cannot reach there, okay? So now I must say, if B is actually true, that implies that's the case, okay? And similarly, if I actually execute S2, what does that mean? That means B actually failed. It's not the case that B is true. So that means I have not B. Given that this is the case, then I can actually establish this weakest precondition. Now, how do I link these two things together? What kind of logical operator should I use? I got two choices for you. Either conjunction or disjunction. Yuzang?
It should be a disjunction.
It should be a disjunction. Okay, let's try that first. If you say disjunction, that means either branch will work, right? You're saying that, let me give you some example over here. How about just do one example? Let's say over here. Let's say if, else, and. Let's say the post condition I want to establish is x is simply larger than 0. I want x to remain positive, let's say no matter what, right? Now over here, you have basically x is assigned to, I'll make it very extreme. How about that? Let's say x is simply assigned to 3. Okay, let me put some Boolean condition here. Now let me just a b over here, any Boolean condition. Okay, if some Boolean condition is true, I'm going to execute x is assigned to 3. Otherwise, I'm going to assign x to be minus 2. Okay, now the question is, what is the weakest precondition for the entire program to establish x larger than 0? Entire program. The entire program actually should accommodate both branches, right? Now, what's the, let me say this is branch number 1. What is the weakest precondition for x assigned to 3 to establish x larger than 0? Over here. So WP for x is assigned to 3 to establish x larger than 0. What is the weakest precondition? True, because I simply replace x by 3. 3 larger than 0 is always true, right? So this one is simply just true. I can just put true over here for now. Okay? In some ways, like one branch is simply just true. And then I say that, what about the else branch? For the else branch, what's the weakest precondition for x is assigned to minus 2 to establish the same post condition? What is that? It's false, because if I replace the same x simply by minus 2, I got minus 2 larger than 0, which would be false, right? So one weakest precondition. So for this branch over here, the WP is simply just true. For this branch over here, the WP is simply false. But now overall, what should be the weakest precondition for the entire program? According to what you said, we'll do disjunction, right? Because you are basically, think about what you really meant when you say disjunction. That means either branch, if either branch can establish the post condition, I'll be fine. However, at the runtime, you have no control whatsoever, because B might just evaluate to be true sometimes, and it might evaluate to be false sometimes. So you got chances equally to either go to this branch or this branch. So if you want to guarantee the entire program, which can go to either branches, will always establish the post condition, you better put something not this weak, right? You better put conjunction. Okay? So guys, that's kind of the rationale behind why you want to do conjunction over here. That is to say, I want to make sure not only that the first branch can establish the post condition, but also the second branch can also establish that. So both. Okay? And then you should also notice that the important thing is we should really put some antecedents over here to say that if I can reach the first branch, that means B must be true. If I can reach the second branch over here, then that means B must be false. So these are the useful information we can use. Okay? So this is kind of the sketch of the idea, but you should really know why we are using this conjunction over here. That's really important. Right? It's a good try. Now, if you go back there to see the rule, so this is the second rule we are learning. Okay, let's read it again. On the left-hand side of the equality, we are trying to calculate the WP. And the program we are considering is an alternation. It's either go to S1 when B is true, or we go to S2 when B is false. Either way, right? So now we got two possible branches. And we say that the weakest precondition for this conditional behavior to establish R would be a conjunction. The conjunction is going to consider that given that B is true, then you must satisfy the weakest precondition for S1 to establish R. That's behavior number 1. And then for behavior number 2, similarly, when B is actually false, given that's true, then you have to establish the weakest precondition for S2 to establish R, you know? Conjunction. Guys, any question here? Okay? Yeah, there's something you have to also think, maybe beyond the classes. I'm just trying to give you some guidance for you to think a little bit more easily. Okay, that's just an English description of what I just said. All branches. Okay, so now, so this is just basically just put the precondition and postcondition into play. Okay, now, let's say if I give you a program like this to say the program is simply overall is an if then else structure, right? If this, we do that. If not this, we do other things. Given that the precondition is Q, and we want to establish R eventually, how do we prove that this program is correct? What we gotta do is, we have to, again, several steps, right? We have to calculate the weakest precondition for this entire program to establish R. And then to make sure the existing precondition, which is Q, is no weaker than that weakest precondition, right? So we follow the same pattern here. Okay, so now that's what you will see. So now you can see that if B is actually true, in the context of the first branch, we actually got Q and B as our precondition, right? So we can strengthen that, okay? And otherwise, we got not B, okay? And now finally, so how do we prove this? You got to prove two things, okay? You want to make sure you got both branches, right? The first branch is going to be S1. The second branch is going to be S2. For both cases, you want to establish the same postcondition R. But the precondition for S1 and S2 to start with is a little bit different. The main difference is one is B, the other one is not B, okay? And then that's actually basically what you're going to prove, just implication, okay? Guys, any immediate questions for me before I move on? If there's anything you want me to explain again. Okay? Yes? Oh, that's a good question. So what Dusan's question was, what about if it's a very good question. Let me just to address your question, let's go back. I want to go back to two places. Let's first of all go back to the original page I just said over here, right? As I said before, what we really want to prove is the existing precondition over here is no weaker than actually the weakest precondition we calculate, whatever it is. We know very well false implies anything, okay? So now the thing is, what if our precondition is simply false? False implies anything, right? That means it doesn't matter what the WP we might calculate in the third step. In that case, in the fourth step, false is going to imply whatever WP we calculate from step number 3. So we always get correct program. However, a program being correct doesn't really mean it might be useful, right? So I want to draw your attention to one previous slide. I want to go back there very quickly. So if you remember this slide over here, where I talk about different possibility for the pre and post conditions. Okay, this slide here, okay? So now if you look at that, bullet point number 2, when we have the precondition being false, that's exactly the situation you're talking about. So that means the clients will never get a chance to use the feature. So that means we'll never be able to tell if the program is correct. Well, that means it's always correct. You never get a chance to testify, right? So that's actually correct, but useless. It's possible, theoretically speaking. So in theory, you should not have any, usually, typically speaking, you don't really have any extreme like this. Either precondition is true, which means all inputs are fine, or all inputs are not fine. You should really have somewhere in between. That's typically the case. Okay. Let's go back. Now let's go back there and then try to see one example. Okay. Let's say we have this. Let's have a look at this program over here. I'm going to use iPad, I think, okay, to get more focus. The question is the same. We want to know if this program here is correct or not. Okay. By the way, you might have noticed that there is one construct of program which we haven't discussed so far about the WP. You can see there's a semicolon over there, right, in both branches. For example, we say that basically we want to determine x and y, which one is larger, basically. Okay. So now, if x is happen to be larger, we'll set it to be bigger. Otherwise, y will be bigger. Okay. So now you can see that for the first branch, we say bigger is assigned to x, followed by smaller is assigned to y. Right? You can see the semicolon in between. So that's so-called a sequential composition. meaning that we're going to execute the program sequentially, one after the other. That's something we haven't talked about so far, but that's okay. We want to do in just enough so that you can see how we can apply the rule for alternation for WP, just enough, okay? Now, if I give this to you, how can you apply what we learned from before, the WP, right? Let me just remind you what the rule is, first of all, very quickly, okay? So the WP, how about you just switch back and forth so I can save some writing. Okay, if you have that, how about this one? Okay, that's what we learned. The WP for an alternation over here is for the first branch and for the second branch, both to establish the postcondition, right? So now, how do we apply that to here? How do we do that? Okay, so now, I want to make sure, first of all, this program over here, let me use a different color. Let me just highlight. So this is the first branch. And this is the second branch. We want to make sure both branches are going to establish the common postcondition. That's what we want to make sure. Okay? So now think about what's going to happen here. If we can reach over here, that means this Boolean condition here, I'm going to just use yellow to highlight that. So this is like a Boolean condition B. Okay? If we can reach the orange part, that means this yellow part is true. If we reach this red part, that means the yellow part is false. Right? Okay, now let me boil it down to what I really want to say. First of all, we start with x larger than 0 and y larger than 0. That's the precondition we start with. Let me use green over here. Okay? And then let's say we go to the first branch. If we go to the first branch, what does that mean? That means we actually get something over here, x larger than y. Okay? So that's the yellow part over here. And then we try to execute the first part. Let me just call the orange part just S1, so I can save some writing. So that means, given this, and I execute S1, and I'm going to establish the postcondition, which is bigger, greater than, smaller. Bigger, greater than, or equal to, smaller. Okay? So that's the first thing I got to prove. And how do I prove this, though? Well, in order to prove this, I got to make sure the weakest precondition for S1 to establish bigger, larger than, or equal to smaller is actually implied by the existing precondition, right, over there. Okay? And another one is over here. Also, I got x larger than 0 and y larger than 0, the same precondition over here. Okay, over here. But now, for me to execute branch number 2 over here. So what's going to be different? The yellow part must be negated, right? Because the yellow part is actually should be false. Otherwise, I wouldn't reach statement number 2. Let me call this S2 over here. Now I got S2 here, and then the postcondition is the same, okay? Really the same. So I can say bigger, greater than or equal to smaller over here. And then what about the missing part over here? How should I put it? I missed something here. X, should that be x larger than y? X less than or equal to y, right? The negation of that, okay? Hopefully you can see that. I'll just put not x larger than y, okay? Like that, okay? So it turns out, and then we want to make sure both are correct. So I'm gonna put a conjunction over here. Both are correct, okay? Not disjunction, okay? Both branches. So if I give you a program like this in the exam, so you can first of all try to simplify that a little bit to say, I want to prove first branch being correct and second branch being correct, and then you can, again, apply differently, okay? Now the question is, once we get to this stage here, for now, we'll get stuck because we simply don't know how to handle sequential composition. We haven't discussed that yet, okay? we're going to talk about it right away, okay? How we can handle sequential composition. And then we can prove this program completely, okay? That's what we will do. So I will go up to here just for this example here. So once we show you how to do sequential composition, it will be an exercise for you to complete this, okay? It shouldn't be too difficult. You're just going to do two things separately, okay? Okay, good. Okay, let's see. Okay, this is exactly what I said, so I'll leave them to you. Okay, good. Guys, any question about alternation, conditional? Again, the intuition is both branches must establish the postcondition, both branches. Okay? Okay, so now, okay, that's basically what I said. Yeah. Okay, now sequential composition. Okay, third rule. So far we talk about assignments, we talk about alternation. Now let's talk about sequential composition. Once we are done with this, we can do already quite complicated program, but we also do loops, so we can do even more useful program. Okay. Let's say this over here. Let's try to understand what's being said over here. Let's say, again, we are trying to calculate WP again. So the postcondition is still R. We want to establish the postcondition R when the program terminates. But now what's the program? It's now to say it can be anything arbitrary as S1, followed by anything that's arbitrary and then S2. S1 followed by S2. So here the S1 and S2, they are the recursive concept. A little bit similar to in your projects when I say expression 1, expression 2, right? E1 and E2 can be as simple as just constant, or they can be as complicated as maybe sum or for all, etc. Okay. So now S1 followed by S2. So now how do we calculate this? Okay, let me just bring to iPad and give you, again, intuition is important. Okay, let me just open a new page over here and then I'll show you the iPad. Okay, let's think about that. We want to calculate the weakest precondition, WP. We have some program S1 over here, followed by, okay, semicolon, just like in Java, okay, followed by S2. And then we want to establish R at the end. So what should be the weakest precondition? This one conceptually is not too hard, but when you want to express it formally, it's a little bit complicated. Okay, let's think about that. I want to know what would be the weakest precondition for me to do two stages of work. The first stage will be S1. The second stage will be S2. Okay? Now, let me ask you this. So this will give you a little bit hints. There is an intermediate point over here. At this point, what should be satisfied? What's this point here? This is the point when S1 terminates, and it's the starting point of S2. Now think about in this way. Let's not worry about overall what should be the answer. Now, if I just ask you the intermediate point, what should be the condition over there? That means S1 already completed, right? So now what should be the property of that? We want to say the starting point, okay, Dusan will take your question or your answer, whatever. Okay, let me just give you a little bit more hints. This is the starting precondition for S2. And this precondition here is somehow established by S1. Which means S1 is going to do the work, and then the ending condition for S1 is going to be the precondition for S2, right? That's kind of what I meant by intermediate point. So what should be the precondition there? Yes?
Two questions is then it follows that S1 establishes a postcondition, it satisfies R as the weakest precondition, and then second question is it S1 implies S2, and then is it like
Okay. Yeah. Yeah. Your second question is a bit too complicated. Let's answer this question one first. I think for your question number one, you were asking, should we say at this intermediate point, we should already satisfy R, which is the post-condition we are aiming for? The answer is no, not in general. It might be too early for you to do that. We don't require that in general, okay? I'll just wipe it out. We don't have to, okay? So now what should be the well, think of this. This is the starting point for S2. Somehow, upon termination of S2, we want to establish R, right? Let's just forget about S1. Forget about it for now. If you forget about it, so what's going to be the condition for S2 to establish R then? We know that, right? It's WP. Okay? So now over here, let me just say what should be this condition here. Starting, let me just use row 1. So what's the starting precondition? So what's the starting precondition? I'm going to write it here. So that would be that would be the WP for S2 to establish R. So this is the intermediate points over here. Okay? That means if S2 can start with the condition which corresponds to the weakest precondition for S2 to establish R, it's guaranteed to establish that. Right? That's intermediate point. Let's get this point straight. And then we worry about the previous stage. Okay? Rob, you got a question? Go ahead. Mm-hmm. Yes. Exactly. So, yeah, that's exactly right. So, as I said before, this intermediate point over here, that means it's the termination points for S1, but the starting point for S2. So, whatever post condition for S1 is going to be the precondition for S2, right? That's what I meant by intermediate points. Okay, now, this is something we know about from before. This is simply over here. We say that the starting point over here must be such that it is the weakest precondition for S2 over here to establish R, first of all. Now, also as Rob noted, this at the same time, this condition over here is also the post condition for S1. Agree? So now, how does S1 establish that post condition? In that case, we can simply do another weakest precondition calculation, right? So let me use a different color. So now, let me just note that this is the starting point of S2. At the same time, it's the ending point for S2, of S1, sorry. Okay, starting versus ending. So now, if the ending point for S1 is actually this condition here, what would be the weakest precondition for S1 to establish that? Just another weakest precondition calculation. So I can just do that. I can say it's going to be WP for S1 to establish that. So that's the final answer. Okay? Now, this is a bit messy here. Let me just use another page to repeat the point. Okay, let me just a little bit cleaner. Again, if we got WP of S1 followed by S2, and then we want to establish some post-condition R. Okay, first of all, we know that the intermediate point over here is going to be the WP for S2 to establish R, first of all. And then we want to make sure this intermediate point is the post-condition for S1. And what is the weakest precondition for S1 to establish that post-condition? It's just going to be another weakest precondition calculation. It's going to be the WP for S1 to establish that. Okay, that's why I said intuitively it's not too bad. All you got to understand is, in this case, the post-condition for S1 is at the same time the precondition for S2. Okay, that's something you got to know. And the precondition for the S2 is going to be strong enough to establish R. Okay? That's all we got to know. Okay, I'll just do one more annotation and see if we got any question. Otherwise, I'll move on. Okay? This is the starting condition for S2 to establish R. Okay? Any questions about this rule over here? But we're going to apply that for sure. Okay, we're going to have some example to see. Okay. Okay, let's go back over here. So now that's exactly the rule. Let's see the English description, which is not too bad. Let's try to read it together. The weakest precondition for sequential composition is such that the first phase, S1, establishes the WP, which is for the second phase to establish the postcondition R, right? Okay. Questions before we do one example? Okay. Yuzhan, are you okay?
Yes.
Good. Very good. Okay, now this, again, let's put the precondition and postcondition into the context as well. Let's say now, given some precondition here, given some postcondition here, and this is our program. Now, if I give you a program like this, how do you prove that this program is correct? Again, separate it into several steps. Step number 1, calculate the weakest precondition for S1 followed by S2 to establish R, which we just talked about. And then to make sure the existing precondition Q is no weaker than that, right? That's exactly what you will see, okay? You can see that over here, this complicated formula over here is exactly the WP rule for S1 followed by S2 to establish R. And then make sure Q is no weaker than that, which means Q implies that. Okay. Okay, now, why don't we do one exercise together? Okay? I would suggest the following. Why don't you take just 1 minute to think about how you would do it? You can either think in your mind or to do it on the paper. Okay, just 1 minute. I wouldn't take too long. And then I'm going to copy this question into my iPad and we'll do it all together. Okay? This one is kind of a little bit more complicated than before. You can see we got a sequential compositions of 3 assignments there. No alternation. Okay, just assignments and sequential composition. And let's see exactly how we can do it. Okay? Take 1 minute, and then I'm going to copy the question to the iPad. Okay? Think about how you would do it. By the way, can you at least get some intuition? Is this program here correct or not? If you actually don't see anything that's straightforward, that's good, because weakest precondition is going to help you, right? We'll see later on today, we'll see a loop example, okay? Maybe on Monday I'll show you the detailed proof, but today at least we get this one done very properly. Okay? Okay, guys, take a little bit more time, and then we'll do it all together. Okay? I can give you a little bit hints. To calculate the WP, you need 2 rules. You only need the rules for assignments and sequential composition. But now the complication about this example here is which one should you apply first, right? That's the existing precondition, and this is the target postcondition, right? And in the middle is our implementation, okay? So now basically we're going to calculate WP for the implementation to establish the red part, the postcondition, and then to see if that WP is somehow implied by the existing precondition. That's a step, okay? Now let's do the WP calculation first. Once it is done, usually it's quite obvious what the result should be, okay? Now, let's calculate the WP. Number 1. What is the WP for the program over there? Let's copy the program down. Temp is assigned to X, followed by X is assigned to Y, followed by Y is assigned to temp. And what we want to establish is x larger than y. We want to know what's the weakest precondition. Once we get a result, the green part should be no weaker than that. Otherwise, the program is not correct. Okay? Now, what should we do? Right? Overall, it's a sequential composition, right? Overall. Okay? Now, we can basically think about what's the first stage and what's the second stage. So you can see that this is the first stage. And everything else will just follow. It's how I will parse the sequential composition. You always want to know what's the first you want to do. Okay? Okay, let's now try to simplify this. If I say, what's going to be the ending condition over here in the intermediate points? I want to know when the first stage, which is temporary, temp is assigned to x, what should be the ending condition for that? The condition must be the weakest precondition for the remaining two assignment over here to establish the postcondition. Okay, let's write it down. Okay, so now I will do the equational style. Okay, I can say now give a reason. You can say WP for sequential composition. In this case, what I will get is I'll get WP over here the same. And then I have the first stage, which is temp, is assigned to x. And then what should be the ending condition for that? Yes. Exactly, for the rest to establish the R, right? Exactly, that's exactly right. So that would be, let me use a different color here. So that would be WP over here for x is assigned to y, followed by y is assigned to temp. For that one to establish x is larger than y. Guys, any questions so far? Are we okay, right? It's not too bad, but you really gotta do it by yourself, okay? It might look easy, but when you really do it, I would say it's okay. Okay, now we do something similar. Now, for this part, the blue part here, we worry about that a little bit later. Let's worry about the red part. Now again, the way I'm gonna parse this is very similar. This is the very first stage I'm gonna do, and this is the remaining stage. I'm gonna keep applying until I reach some base case, which means I don't have any sequential composition anymore, okay? So now, I'm just gonna say again, WP for sequential composition. I'm gonna apply that once more, okay? Now I can say WP, and then the same as before, temp is assigned to x, followed by, over here, this is WP over here, and then x is assigned to y, right? I'm gonna actually apply this part over here, right? Okay, this part here. So now, what's gonna be the ending condition for that? It's gonna be for y is assigned to temp to establish x larger than y, right? So again, let me use a different color. How about green? So now it's gonna be the WP for y is assigned to temp, and that one should establish x larger than y. Okay, and now let me just close that properly. Red and blue. Now you can see what we have done so far. We have eliminated sequential composition at the top level. So now we can somehow simplify things backwards. Which is this? Tell me something. Which is the expression I can simplify the first? Blue, red, or green? Green, right? The green one is not sequential composition anymore. What is that? It is an assignment, right? So now assignment, I will consider that as a base case. Okay? How do I simplify the base case, the green part over there? What should I do? Any idea? Yeah, how do you, yeah, so remember what the weakest precondition rule is for the assignments. We're gonna basically substitute every instance of y by temp in the postcondition there, okay? That's what we're gonna do. Okay, let's do it. Okay, and then let's say, now it's gonna be the WP for assignments. Okay, it's this part over here. So now this part, let me use green over here. Now this part, how do we simplify that? We're gonna say X, okay, let me just do one, that's actually detail. So now we still got WP over here. So we got temp is assigned to X. And then we got red over here, WP, which is X is assigned to Y. Now, how do we simplify the green part? First of all, let's copy down the post condition, which is X plus Y. X larger than Y. Over here, we're gonna replace every occurrence of Y by temp, okay? So that's a rule. So every occurrence of Y by temp. Okay, and then let's close by red first, and then close by blue. Okay, so now let me be a little bit lazy here. So now you can see that what's this part over here? X larger than temp. Okay, X larger than temp. I can actually make it, maybe use a different color here so you can see a little bit more obviously. X larger than temp. Now we only got two colors left, either the red or the blue. Now we can now simplify red, right? So you can see when we expand the sequential composition, we go from left to right. But now when we simplify using assignment, we go backwards. Okay, that's something you should notice. Okay, now how do we simplify this red over here? Okay, let me just, you kind of get it, so I'll get a little bit faster. So WP for assignments again. Now, I know that I'm going to replace every occurrence of X by Y in this particular post condition here, right? So what I will get is Y is larger than temp, right? I'm going to replace Y for every occurrence of X in the post condition there. So what I will get is something like this. It's going to be WP, temp is assigned to X, and then it's going to be Y is larger than the temp. Okay, we're almost getting there, right? Almost there. Okay, one more. Finally, how do we simplify this blue part over here? Again, we can apply the rule for assignments. Okay, how do we do that? Over here, we're gonna replace every occurrence of temp over here by X. That's what we're gonna do. Okay, finally, we're gonna get the Y larger than X. So this is the final answer. So that means in order for you to actually execute this block of implementation to establish the post condition over here, the weakest precondition is Y larger than X. Now, is the existing precondition there, which is true, is that no weaker than Y larger than X? Or, logically speaking, is the following true? Now, I just have a little bit of space over here. So now, the true over here, when I say true implies Y larger than X, is that true? Does that hold in general? No, right? Imagine this. What kind of precondition should I give to this program over here in order for the program to be correct? The weakest one should be Y larger than X. That's the weakest one. However, the existing precondition simply say any program, any input is okay, including when X is larger than Y, right? So this does not hold. So the program is not correct, okay? Okay, let me just give you a little bit more intuition, okay? Now that we know that the program is not correct, think about what we're doing here. If you look at what the program is trying to do, we are basically swapping the value of X and Y. I hope you see that, right? Now, we say that after swapping X and Y, X must be larger than Y. That means before the swapping, it should be the other way around, right? Now, that means it cannot be just arbitrary, just true precondition. It must be that before you do the swap, Y must be larger than X, so that after the swap, X becomes larger than Y, the opposite, okay? So that's after we have applied this weakest precondition mechanically, you can also see this intuition. Okay, any question about this? So we have done this together. So now you can also see that on the slides, that's exactly what I included. Okay? That's a little bit more organized. Questions? That's the minimum I would expect you to do in the exam, minimum. But we'll see something, I'll give you an example and solution, next Monday. But of course, you can see this technique here is not applied. You can see it's not just about IFO. It's about program verification, which is important. You want to know what kind of precondition you need. Okay, let's talk about loops. Okay, so I don't think we'll reach to the point that we talk about the whole triples for loops, but I want to introduce two new concepts to you. How many of you have heard about loop variants and loop invariant? How many of you not have heard? How about not? Not have heard. Everybody has? Okay, it's not too bad, okay. Maybe in 3101 possibly, or in 2011, okay. Okay, but let me just go through some example with you about the loop invariants and loop invariants, maybe from a different perspective. It's more about proving that your loop is going to terminate and also your loop is going to establish something desirable. Okay, now, for example, we're going to actually see how we can prove the correctness of a simple loop where we're going to get loop invariants, we're going to get loop variants as well. Okay, so now, let's see over here. So these are very common sense because we have certainly loops. Only sequential composition and alternation would not be good enough. Okay? However, it's very hard to get right. Okay, so now loops are very hard to get. Done? Okay, good. So now, typically, I would say the problems you might have for the loops, either it's about termination. For example, you forgot to increment the loop counter. That's one possibility. Or you simply got to say after finishing the loop, even though your loop terminates, but the post condition is not established. So these are the two categories of problems. But we're going to see how we can prove these two things formally. Okay? Maybe that's something I will do thoroughly on Monday, but today I want to go at least some concept very quickly. Okay? So you may have infinite loop problems, termination, or you may have off by one error, which means maybe I should have done one more iteration, or I should have done one fewer iteration, right? So this is more about partial correctness. Partial correctness means it's not really about termination, but just about if you can establish something you really want, okay? Also, we also got borderline cases, right? That's also important to handle. You want to handle everything, okay? Okay, also not establishing the desired condition, okay? Now, if you're interested, you can also go to the textbook. So on page 381 in OSC2, basically the point is they try to list 4 different implementations for binary search that's been published, but all of them are wrong. So they actually suffer from either of the problems over here. Okay? The point is, loops are really hard to get right. Okay? But we want to learn how you can actually get things proved or disproved, so you can have some idea about how correct your loops are. So now, how do we prove the loops are correct? Let's see the syntax first, and then we'll see some meaning. Okay? Okay, let's say we have some precondition before we execute a loop, and then so let's talk about IFO, and then I'll show you what the corresponding syntax should be for Java. Let's say we got a from part. The from part is going to be some program over here. I call init, which means well, we want to initialize something. Okay, and then we have some condition over here. So in the case of IFO, the Boolean condition we specify is called the exit condition, which means as soon as this condition becomes true, we're going to exit from the loop. And we're going to see the corresponding loop in Java in just a moment. So the technique we learned can also be applied to the C family language. And then we're going to keep iterating the body of the loop. Okay? And then eventually we want to establish some post condition. So now, how would the corresponding loop look like in C or in Java? Basically, everything is going to be very similar. Okay? you can see that we still got the precondition to start with, and then we're going to execute the initialization step for just once and only. And then we have the while loop, for example. Let's say while loop. And then you can see that I put a negation over there, because for the meaning of the while loop, that means as long as the condition is true, as long as we are not going to exit, we're going to stay in the loop and keep executing the body of the loop. That's why I put a negation there, right? And then you can execute the body for as many times as long as not B remains to be true, okay? And then eventually you want to establish the postcondition R. So these two loop structures are completely equivalent, okay? But for the rest of the lecture, we're going to focus on the left-hand side, because in the case of the IFO loops, they also support invariants and variants natively. So you can also have the runtime assertion checking to work for you. So I'm going to go over some examples with you. Okay? Okay, so now again, in Java and C or the C family language, whatever condition is specified is a state condition. And in the case of the IFO, if you want to get equivalent loops, you'll simply negate the state condition. Okay, that'll be exit condition. Okay, it should be fairly straightforward. And then, now, how do we prove the total correctness of loops? Now, let's recall what's the definition for total correctness. It's basically partial correctness plus termination. So we're going to prove termination, and then, assuming that the loop is going to terminate, are we going to establish the desired postcondition? So these are the two things we want to know how to prove. Okay, let's see how we can specify contracts for loops. Okay, let's see that. And I'll show you briefly how the runtime assertion checking is going to work for this syntax here. So we say that from some initial step only once. And then this is a new one. So now you can see that invariant keyword is not at the class level, it's at the loop level. So this simply means after the initialization step over here, I'm going to establish something. And that invariant, which is so-called loop invariant, is going to remain true as long as I'm in my loop body. So it's going to be true. Okay, and just like for postconditional invariants, you can also put some tag over there. Okay, and then it's just a Boolean condition, I. Okay, I'll just call it I. And then we can say that until the exit condition is true. Okay, and then we're going to loop for as many times as possible, and each time we simply execute the body of the loop, S body. And now, at the end of the loop, we also got another thing to check. This is something called variance. Variance simply means it is something that keeps changing, okay? But it's gonna has a boundary of to what extent it can change. So now for the variant over here, it's actually an integer expression. By the way, the invariant over here is a Boolean condition. It should always be true. Otherwise, you got looping variance violation. On the other hand, over here, for the variance over here, it's an integer expression. Intuitively, this integer expression here should tell you exactly how many times more are you going to iterate through the loop, how many more iterations you're going to go. As soon as this variant v expression here becomes 0, that means no more iteration, you should exit from the loop. So that means we're bounding the number of iterations for the loop, okay? So now let's just talk very briefly, since you have maybe learned about both concepts, let's brush up, and then we'll do one example together. Okay? So let's talk about looping variance and loop variance. Looping variance should be something that keeps being true, and then loop variance should be something that keeps changing until it reaches 0. Okay? Let's just go over very quickly. The invariant is a Boolean expression for partial correctness. Looping variant is not for you to prove termination. No, it's only to say, given that it terminates, are we going to establish the postcondition? Now, how do we specify the looping variant? I will try to give you one example in full detail, and also give you some more, maybe quick example on Monday. But typically, you want to make your looping variance a special case for your postcondition. That's to make the proof easier, and also to make your contract more explicitly specified. Okay, we'll see example. Okay, one example right away, actually. So let's say this is the postcondition. Let's say we are trying to run through a loop for a query. And the query is going to return an integer from the input is simply an integer array. We say that the result, the return value, is the maximum of the array. So that's the post condition. Okay? Now, we want to define some invariant condition so that it's going to remain true. Keep remaining true as we are going. And then when the loop terminates, the expression will still be true. But that expression is going to be equivalent to the post condition intuitively. Okay? Now, I'll give you some, the example we're going to go over is very straightforward. Let's say we have an array of integers. We simply go from the leftmost index and gradually scan through the array. Okay? Let me give you some idea on the paper quickly. Okay, I'll go through this diagram in just a moment. Okay, let's say this is the input we have, input array. So now, first of all, talk about the post condition. What's the post condition? We are saying that the result, which is supposed to be the maximum, is going to be the absolute maximum as far as the entire array is concerned. Entire array. So this is a post condition. Okay, just to say that the result should be larger than or equal to every element in the array. Okay, now how do we specify the loop invariance? As I said before, it's going to be a special case of the post condition. Let me just draw the same array and then show you the idea. Of course, if you want to do a typical loop, you will simply have a loop counter, input array, and then what would be the loop invariance? Okay, let's say this. Let's say if currently I'm dealing with index I. Let's say I is a loop counter. Okay. So now, as you know, in order to find out the maximum, you have to compare the temporary maximum against the current value. If the current value happens to be greater than the temporary maximum, you're going to replace the maximum, right? That's what you will do. Very fundamental thing to implement. So now, let's say if I finish the current iteration, that means this part of the array has been scanned through by my feature or my method. Okay, so far. The remaining part I'm not sure because I haven't dealt with them yet. Okay, so now what does that mean? The loop invariance will be depending on where I is. Okay, so that means result is the maximum from, for example, A0, A1, all the way to only AI. What about AI plus 1? I don't know because I haven't scanned through them yet. It's only this partial array. So that means every time when I try to move on with my loop with one more iteration, I'm growing this green area over here by a little bit longer, right? So gradually I grow that. You can see the index over here is going to grow as well. Eventually, once I finish the last iteration, the I value is going to be exactly one more than the last index of the entire array. In that case, I'm going to cover the entire array. So the loop invariance would just be equivalent to the post condition. Okay? That's the intuition first, and that's the example we're going to follow through in iPhone, in program. Guys, any question about this intuition here? Okay? So the red part is basically the post condition, which covers the entire array. Okay? And the green part is the loop invariance, which means the green part, basically, the expression itself is going to change. Let me just specify that. Okay? Very quickly. In universal quantification, we can say that for every j, we got I as a loop counter, such that, let's say we got lower, which is 1. Okay? 1 less than or equal to j, and now I will say less than I. I'll tell you why it should be strictly less than. We'll see example where it is not less than. And it is the case that result is larger than, which is the maximum, larger than or equal to a j. Okay, this is array A. So this is the loop invariance we have. So now we're going to, and every iteration, we're going to grow the counter value to be one larger than before, right? So eventually, the I over here, eventually, let me show you here. So eventually, this I loop counter here is going to be exactly the same as this last index over here. That means we're going to cover the entire array eventually. Okay? But this expression here must be true always. Okay? There shouldn't be a single moment where this is false. Okay, so now this is informally what loop invariant should be. So we say the result is the maximum of the part of the array we have scanned so far. Okay, what's beyond I, we don't know. But before I, we know we have scanned through them already. The maximum we have got so far is guaranteed to the temporary maximum. Okay, okay, so now what should okay, so after the initialization step for the loop, we should really establish the loop invariance. Once it is established, it should remain true between each iteration. And then what about the variance? So variant is, just from the literal meaning, variance simply means something that is going to keep changing. Okay? So variance is going to be an integer expression as opposed to a Boolean expression. It's going to tell us when to terminate the loop. Okay? Now, it tells you exactly how many times the number of iterations that remain to be done. Okay? So now you can think of, if I have an array of size 4, that means the initial value for the variant should be 4, telling me there should be 4 iterations to be done. After the first iteration, it should decrease, the variant result should be decreased from 4 to 3, 3 to 2, 2 to 1, 1 to 0. Once I reach 0, that means I must terminate now. So somehow the variant value will bound the number of iterations. Okay, decrease every time, and then it should be positive. It should never go below 0. Once you reach 0, that means you should really exit. Okay? Now, finally, why do we need these two things? For loop variance, we want to prove termination. For loop invariance, we want to prove partial correctness. Combine them together, we got total correctness. Okay? Okay, a few more minutes, and then we are done. Questions? Yes. You mean, does it check? Wait, say that again. I don't quite get your question. Sorry? Can you repeat your question again? Yeah.
Does it check before or after?
Okay, good, very good. So now let me just answer this question and then we're done. Okay, I think it's worth stopping here, and then we'll continue on Monday. Okay, the question was, how is invariant gonna get checked? Okay, so now I'm gonna use two different diagrams to show you. Give me one moment. I'm going to show you the syntax over here first. Okay, so this is the syntax where we got invariance. Okay, so invariance is over here. Also, we got the variance. Okay, how is it checked? Okay, let's go. I'm going to use arrow to tell you the flow. Let's say I use red. Let's say first of all, we execute the initialization step only once. And then we check to see if this is true or false. If it is false, loop invariant violation right away, which means it cannot establish that. Okay? Established. And then if it is established, and then we check to see if the exit condition is true or not. That means should we exit from the loop? That means we don't even enter the loop for the first time. Okay? Let's say exit or not. Let's say we don't exit. In that case, we go ahead and do the very first iteration over here. After that, we're going to evaluate the variance over here, okay, to see if it is still larger than 0. If it is larger than 0, that means more iteration to do, okay? And then, let me use a different color. And then after this, we're going to go back. Guess where should we go back? Should we go to the initialization or somewhere? Invariant, exactly, because now it was established before the first iteration. We want to make sure after the first iteration is maintained. So now after this, we're going to go back to this invariant over here. And then we want to know if the invariant is maintained or not. Let's say it's false, loop invariant violation. If it is true, that means it's maintained. Then we go into the loop, and then we check to see if we should exit from the loop. If we shouldn't, execute the second time. Okay? If we should exit, we still got the loop invariant maintained, right? And then we just go exit the loop. Okay?
After that, it's not exiting, but the variant tag is still not 0?
I see what you mean. You mean you exit, but your variant value is not 0, right? No, you'll get variant violation, which we'll see. on Monday, okay? So guys, I will refer you to one more diagram and then we are done, okay? I want you to look at this diagram very carefully. So this diagram really visualizes how things are going to work, supposedly. Okay, I'll go over that very quickly. So now, so let's say we're starting from some precondition for the loop. We try to execute the initialization step for the loop. After that, we should establish the loop invariance. You can see that the way this diagram is to say the invariance is going to be assertion, which is going to be a set of satisfying values, satisfying states. So now you want to make sure every iteration over there onwards is going to within the region of the invariance, which means we maintain that, right? So now, as soon as you actually try to exit, so the exit condition is over here. So that means whenever you enter this exit condition over here, you can see we are still within the range of invariance, right? So they're overlapped, which means you exit doesn't mean you can violate the invariant. It should still be maintained. At the same time, there is another condition you want to satisfy, which is the post condition. So you can see the ending states over here. Let's say if I end over here. So this is an intersection of three things. So we got loop invariance, we got the exit condition, which means terminates, and also we got a post condition satisfied. So there's an overlap of three things together. Okay? So that's how you should conceptually understand this. But now, how do we turn this conceptual thing into math or triple? So that'll be the final topic for this course on Monday. Okay? So I'll see you on Monday.